Today we're going to talk about prime factorization. To start with, what's a prime number? A prime number is any number that only has two distinct factors. So for example, 2 is a prime number because its only factors are 1 and itself. 3 is a prime number because its only factors are 1 and itself. 8 is not a prime number because it has 1 and itself as factors, but it also has more than 2. So 8 is not a prime number. Some examples of the most common prime numbers you'll see are 2, 3, 5, 7, 11, 13, and on and on and on. You'll notice 2 is the only even prime number there is. If it's not a prime number, it is called a composite number. So like we just did with 8, a composite number is any number that has more than 2 distinct factors. Remember, distinct means different or unique, not repeating the same number. So composite numbers could have 3 factors, like 25, which has 1, 25, and 5. It could have loads of factors, like 100. So long as it has more than 2 distinct factors, it is called a composite number. There is one number that is neither prime nor composite, and it's the number 1. Because 1, the factors of 1 are 1 times itself, which is also 1. And remember, to be prime, you need 2 distinct factors, which mean 2 unique. 1 and 1, that's the same. So the only number that's not prime or composite is number 1. Alright, so what is prime factorization? What does it have to do with prime numbers? And what is a factor tree? Well, prime factorization is the way you can write the value of a number in a multiplication sentence using only prime numbers. Well, what does that look like? Let's do an example. Let's say we have 25. To find the prime factors of 25, I'm going to use a factor tree, which looks kind of like this. Sort of like a factor rainbow, except instead of any old factors like 1 times 25, I'm only going to look for prime numbers. I know 5 times 5, that equals 25. When I see a prime number, I circle it. 25 is composite, so I don't circle that. So the prime factorization of 25 is 5 times 5, or 5 to the power of 2. Let's try another one. Let's go with a bigger number. How about 140? Now, the nice thing about factor trees is there are lots of different ways you could do them. You could start out with a couple different breakdowns of 140 and you'll still end with the same answers. So I'll model 2 different ways. Gotta give myself a little more space there. Okay, one way I could make 140 is I could say, well, 2 times 70, that equals 140. Oh, 2 is a prime number. I'm going to circle that. 70 is not. It's composite, so I'm going to keep breaking that down. What times what equals 70? 2 times 35 equals 70. 2 is a prime number. I'm going to circle that. 35 is composite, so I'm going to keep breaking it down. Well, what times what makes 35? 5 times 7 equals 35. 5 is a prime number, so is 7. So I think that my prime factorization for 140 is 2 times 2 times 5 times 7. Notice I write it in order from least to greatest. So the smallest prime number, 2, starts the list, then it goes in order. I could also write this as 2 to the power of 2 times 5 times 7. Well, what if I didn't see the 2 times 70? Would I still get the same answer? If I have a number that ends in a 0, my personal favorite way to break it down right away is to say 14 times 10. That looks very different from the tree I did on the left, but we'll see if I still get the same answer. 14 is composite, so I'm going to continue to break it down. 2 times 7 equals 14. 2 is a prime number, 7 is a prime number. 10. Well, 2 times 5 equals 10. 2 is a prime number, 5 is a prime number. Going in order from least to greatest, sometimes it helps me to cross them off as I go. I have 2 times 2 times 5 times 7, which is the same thing that I got with my other factor tree. So no matter how you choose to start your factor tree and break it down, you should arrive at the same final answer. Oops, that's not supposed to be a 3. 2 to the power of 2 times 5 times 7. Let's take a look at one more type of problem. So this question is asking us, what is the prime factorization of 66? And I've got some options. 6 times 11, that equals 66. 60 plus 6, that equals 66 too. 70 minus 4, oh, that's also 66. 2 times 3 times 11, also 66. So it's not a question of which one equals 66. It's a question of which one is actually the correct prime factorization. Well, I know prime factorization is a multiplication problem, so B and C, while they do equal 66, are not correct. So now I'm looking at A and D. Both of those are multiplication problems that equal 66. But what I need to really watch out for is I'm looking for prime factorization. 6 is a composite number. I can continue to break that down into 2 times 3. So 6 is not prime. That is why A is not the answer. 2 times 3, that equals 6. Those are the prime factors of 6. Times 11 equals 66. So when I'm looking for prime factorization, I need to make sure that all the numbers in my multiplication sentence are prime numbers. The last thing to look out for is, remember, if you see something like this is the prime factorization. It does not mean 6 times 10. No way. This really means 2 times 2 times 2, 3 times, 1, 2, 3, times 5 times 5, 2 times, 1, 2. When you multiply this whole thing together, that will give you the number that this is actually representing. So 2 times 2 times 2 is 8. 5 times 5 is 25. 8 times 25 is 200. So watch out for your exponents.